Okay. Yes.
Can we just open the?
Yeah, a little bit if you,
Yeah.
yeah. Okay, this should say 4.2. This is what we're on. So just, we're on 4.2 right now. No, it's not. These are old notes. I just forgot to change the title. So 4.2 is about the atom, the structure of the atom, and different experiments on how they discover what the atom looks like and different parts of the atom. So to define an atom, it's the smallest particle of an element that retains the properties of that element. So what that means is that if you were to take, say a bar of gold and cut it into two pieces, now you have 2 blocks, and cut the block again into 2 pieces, keep on cutting the block smaller and smaller and smaller, you get to a point eventually where you're down to one single gold atom. And that would still be gold. But if you were to make that atom fall apart, you would not have gold anymore. You'd have neutrons, protons, and electrons. So an atom is defined as the smallest bit of matter you can have where it's still that element, whether, gold, silver, platinum, etc. So after you were to split the gold atom into its constituent parts, neutrons, protons, electrons, it would not be gold anymore. It would just be the little particles. These pictures show you a computer image of atoms. So we can't take a picture of an atom. We aren't able to do that. We don't know if we can ever do that. But at this point, we can use computers to model what atoms probably look like. So this shows you nickel atoms, and each little mountaintop is the atom. And then you can see down here, the yellow honeycomb structure are carbon atoms.
Are those the 2 kinds?
There's all kinds of different ones, but there's just 2 examples of atoms you might see, but there's all kinds of different examples of atoms, but these are just 2 ones that we have seen.
Is the black part the atom or
Mm-mm.
the yellow?
Yeah, the yellow parts, yeah, and the black is just empty space. So carbon atoms are in hexagons, not always, but this is one pattern they can have where it's hexagonal shape. And so you have 6 carbon atoms to make up a ring, and the black part is just empty space. So there's one right here. So the peaks are the atoms right here, and then the valleys are just empty space.
What is the red?
The red?
Yeah.
You mean like this area right here?
I think it's just shading.
Do you like that area? That's just part of the atom. Like, so atoms, we'll learn later on, they're not really spherical the way we think of them as being spherical. They're not just individual balls. They're not, the boundary between where one begins and one ends is not really sturdy. It's not really definite where that boundary is. So the electrons move all around the area. It's kind of like if you move your hand really fast, you see a blur. That's kind of what electrons do too, where they move so fast that you get this blur or this cloud of where they might be. And that's really what we're seeing in this picture, is just movement of electrons so quickly that you have this boundary of where they usually are, but they can be anywhere within this boundary. So we'll talk about experiments that helped discover the parts of the atom. So Dalton, 1800, formulated his atomic theory. He said atoms exist, and he talked about their properties. But he didn't know what was inside the atom. He thought it was just full of just matter, but he didn't think it was anything smaller than the atom. He didn't know about protons, neutrons, and electrons. But when somebody asked Getch about Dalton and how he knew they were balls, and the reason why he thought they were balls was based on the planets. The planets were spherical shaped, and he assumed, that was a perfect shape, that God made the sphere the perfect shape. And because heavenly planets were spheres, he assumed that the atoms would also be spheres. because that was the simplest, most perfect shape he could think of. And so that's why he thought so, but he had no evidence to show that they were spheres. He just based it off of that, of seeing the planets. So William Crookes in the late 1800s, he used a partial vacuum and he electrified it to see what would happen. And so this down here is a vacuum tube. It's mostly empty space, but it has some air in it. And he electrified it to see what would happen. So electricity ran through the gas tube, and he had one end right here. He had the negative end right here, the positive end down here. And what he assumed is that particles from the negative battery terminal, the cathode, traveled through the gas and hit the wall of the tube. So he assumed what was happening is that particles are being moved outward from this terminal right here and going outward and hitting the cross. And if that were true, there would be a shadow cast on this side where the particles are hitting and not going through. And so when he did this, when he added electricity to this tube, it glowed. It glowed green. And so based on that, based on the glowing that he saw, he assumed the glowing was particles that were coming off from the atoms. He assumed the atom was splitting, that particles are coming off the atoms, which was making it glow green. And to prove that they were really particles, he made this cathode ray to see if there was a shadow cast on the wall, because if there was, that would prove that there actually were these particles that were being hit by the cross and not passing through. This is similar to what we see in fluorescent lights. It's really the same kind of thing, where you have almost a vacuum tube in the light bulb, just a few particles of air that are electrified and it glows at that point. It's how we make TVs too. Basically, the old school TVs are the ones that are really, really big. They are basically gas tubes that glow different colors based on electricity going through them. So this led to the invention of TVs and light bulbs.
Is that
Dangerous
dangerous?
for a TV to have a gas tube in it? No, because this gas is not explosive. Like there's different kinds of gases, and this gas will not explode or even light on fire. So it's very, very safe. Now there can be mercury dust in these tubes. And so if you have one break and the dust goes into the air, if you breathe that in, that could be a problem. But besides that, they're very safe.
So how are new TVs made? And
There's
like,
different ways. Some have liquid crystals that change color. LCDs are little crystals. So that's one new way that they have them. That's the one that I'm most familiar with. I know there's other technologies too available, but that's the one that I know most about.
what about computers and iPads and stuff like
I think those are also LCDs.
Do you know what they're using on like the newest stuff? Because they recently came out with 8K.
Yeah, I don't know what that is. I need to look up and see what that is. Because I've heard of it, but I don't know how that's made.
Wait, can you go back for a second?
Let's see, I'll look that up and see what a 4K TV or 8K TV is. So 4K stands for just the resolution, 4,000 resolution. I think you said there's an 8K TV.
What's the resolution?
Resolution is how many pixels you have. So if
So
you
like
have,
older ones have like
Like 1080p.
And
That's less pixels, so like 10, yeah, 1080, so
What's
1080.
like Minecraft?
No.
Yeah, but like 640 probably is Minecraft.
Is that why when you zoom in on a picture a bunch, it'll look square?
Yeah, because you have less pixels. Yeah, that's right. You're looking at less pixels. So you can see right here, this bottom picture shows you what it looked like when when it glowed, and the cross obstructed the particles, and so that was evidence that they really were particles that were being formed. So he changed the kind of gases in the tube. No matter what gas he put in the tube, it still glowed, but he got different colors. He concluded, though, that because he got the same results every time, that they always glowed, that this must be a particle found in all kinds of matter, that every atom must contain this particle, no matter what it is. So this is evidence that atoms have smaller particles that you can pull out of the atom.
So how did it make it? Oh, wait. How did it make a shadow? Did he have to turn off the lights to
Mhm.
filter the shadow?
Yeah, he turned the lights off. And then the particles are coming from this end right here. They're shining light through. It's kind of like having like a flashlight, where the flashlight's coming from right here, and it's shining this way.
So even though there was no light in the room, he used electricity and shot particles as something to make a shadow?
Exactly. Yeah, so the electricity was creating the light. The electricity hitting the gas made light. And that's how we get light bulbs. Like these light bulbs up here, it's the same exact principle. It's what he did in this experiment, where electricity is shooting gas particles, they glow, and that creates the light we have in this room.
So then how come when you like videotape a light, like you can see the like the different layers, I guess?
Yeah, because it oscillates. So electricity is not constant in these. It goes back and forth, on and off, on and off, on and off again. And so light is not constant in the room. It actually turns off and on very quickly. We're just not aware of it because it happens so fast. The dimmer the light, the more often it's turned off. And so if you use a dimmer switch where it goes from bright to dim, all you are doing is making the periods of dark more constant, more frequent. And so it might be dark, say 20 times per second, but then if you make it dimmer, it can be dark 40 times per second. And so that creates what we feel as a dimmer light. We not aware of it turning off and on so fast, but it happens.
So how come like a camera can capture that?
Because it's able to process more images per second than we can. We can take in 4 frames per second. And that's it. And so movies show us about 24 to 30 frames per second. And so we can't see all those frames. And so to us, it looks like it's moving. With lights, the same thing. If it flickers, say 30 times per second, well, we can't see that. And so we're not aware of it. It's kind of like, if you have like you move your fingers back and forth really fast, you're not aware of it if you go really fast because you can't pick up those images. And so that's what's happening too with the lights turn off and on really fast.
So what does the glowing have to do with this heating of like particles?
The what?
The glowing?
Oh, the glowing. So what happens is that electrons are shooting off the atom. And as they shoot off, they create a glowing light that we're seeing. And so once he concluded these are particles coming off the atom, he wanted to know, well, what are they? What do they do? And so he did different things to see what they were. And magnetism was one of the first things he tested on it. So he took a magnet and moved it towards the beam. And he saw that the light beam curled by the magnet. So normally it's just straight across, but the magnet made it curl.
Could we do something like that?
Actually, we will. I actually have the equipment to show you this today.
Oh, is it that?
So, well, I'll explain in a second. It's related to that because basically what this is also what he made. I mean, this is basically the same thing. It's mostly a vacuum sealed tube with some gas in it. There's neon gas, argon, and that creates different colors that you see.
Is that
So
one of those things where when you touch it, it goes to like your fingers?
exactly, yeah,
Is it called like a plasma ball?
that's right. Yeah,
But will we do something like?
yeah, like more like this. Yeah.
Like that?
Yeah, I have something like that that you can see today. And so the magnetic curling that he saw was evidence that there was electricity. Electricity responds to magnetism. And so that showed that this was a charged particle. Now, he didn't know what charge it was at first, but he knew it was charged. And so at first he knew it was charged. Now to see whether it was positive or negative, he did more experiments. Let me change this so you can see it better. These notes got moved around a little bit. So the top bullet point you already wrote down, but the bottom bullet point, you should know that then he put it to electric field. So at first he put it in a magnet where you have the north and the south poles. You can see that it curled. Then what he did is he moved on to electricity. He had a positive plate and negative plate to see which way the electricity moved. And so what he noticed is that the beam moved towards the positive end. Do you see how it's curling up to the positive plate?
Who did this?
William Crookes. And so if it moved to the positive plate, what charge would it have to have?
Negative.
That's right, opposites attract. So opposite charges attract, so positive attracts negative, and vice versa. And so if it moved to the positive plate, the beam must be negatively charged. And so he knew that it had a negative charge based on those experiments. Now, how much of a charge did it have? Well, he couldn't answer that question, but he knew it was a negative charge. So far he confirmed that these are particles, that they have mass. He didn't know how much mass they had, but he knew they had mass. And he knew that they had a charge, a negative charge. And he knew they are smaller than the atom. So he discovered the electron. No, he didn't. He did not name it that. That's what he discovered.
What did he call them?
Cathode rays is what he called them, because it came from the cathode end. You have the anode and cathode of the battery, and so he called it cathode ray because that's where it came from. Did everybody have these down?
No.
After William Crookes, J.J. Thomson came along, 1897. He did a lot more experiments with this. He gave it the name electron. He was able to find the mass of these particles. And what he discovered is that they're about 2,000 times lighter than hydrogen, which is the smallest atom. And so these are a lot smaller than the atoms. And so this is more evidence that these are particles that make up the atoms because they're so small compared to the atom. He confirmed what William Crookes was saying. He confirmed that these were breaking off from the atoms and were in the atom, but were coming off from the atom to create the glow. Did we have those done? Oh, sorry. Don't worry about that diagram, just the bullet points.
Is that E divided by MC?
No, it's ME, that's the mass of the electron,
What's E?
the charge of the electron. And so we took the charge divided by the mass of the electron.
What is that equal?
I forget what that is. He found a ratio between the two. In the next slide, they might see that, you might see that. But he just got the ratio of the charge versus the mass of the electron. So it doesn't show it on here either. You could find it though. You could, basically it's gonna be 1.6 times 10 to the 19th and divide it by the mass 9.1 times 10 to the 28th. That's what you would have for that. So about 10 years later, after J.J. Thomson named the electron, Robert Millikan did experiments to further understand the mass of the electron and the charge of the electron. And so what he did is he got an exact measurement of the charge of the electron. He also got an exact measurement for the mass of the electron. So Thomson got a ratio of the two. Did you get that?
Well, I was asking what the numbers were.
Oh, it was, it's 1.6 times 10 to the 19th. And then the mass on the board right there, 9.1 times 10 to the 28th. He did, that's what J.J. Thomson found. Or Millikan, yeah, negative 28th, yeah. So that was just a ratio that he got. It's probably a pretty small number, isn't it?
Yeah, it's like 1.75824176 e to the negative.
Yeah, I mean, it was a pretty small, but that's what he determined. And then Robert Millikan got an exact mass and exact charge of the electron. And he found it to be 1840 times smaller than a hydrogen atom. It's almost 2,000 times smaller than the smallest atom. And he got the mass of it. And he did that based on this experiment right here. So he took some oil droplets and shot a fine mist of them into this container. They fell down and there was an X-ray beam that moved the electrons from the oil out to make them charged. So the oil became charged as it went through this X-ray area. You had this charged plate right here. You had a negative and a positive end of the plate, negative down here. Well, these became negatively charged. And so that meant that this negative end right here would repel them and keep them hovering above. So if he could make them suspend in the air, he could match the negative charge of these particles by them being suspended in the air. And he could also measure their weight based on the force needed to keep them suspended. So based on the charge and the force to keep them suspended, he could measure the charge of one particle and the weight of one particle.
So what do they do with the protons and the neutrons and the neutrons?
Oh, the protons and neutrons, they didn't know about those at the time.
So how can they determine the mass
Of the electron?
without knowing the, like, their protons and neutrons in reality?
Yeah, because they were pulling out just the electrons. That's all they were looking at was just the electrons. They didn't look at the other things yet because they couldn't, they didn't know about them.
So the protons and neutrons don't glow?
No, they don't. Only the electrons glow. No, you don't need to draw it. You don't need to really know it in detail either, just know the basic thing. That he found the mass of the electron and the charge of the electron. That's all you need to know about Robert Millikan. So based on that experiment, now Thomson knew that matter was neutral. We all know this because if you touch matter, you don't get shocked. if you don't get shocked, it has to be neutral. Only things that are charged give you a shock. And so if matter is overall neutral, and he knew there was a negative charge to matter, there must be a positive counterpart to counteract the negative charge, so that overall it's neutral. So he concluded that there must be a positive part to the atom too that he wasn't seeing. Now, he never discovered what the positive part was, but he knew it existed. But he was the one who named it as an electron. So based on his discovery, they made a new model of the atom. Before Thomson, Dalton just thought it was just a blob of matter with nothing inside besides just, just solid. But Thomson said, no, there's actually particles that make up the atom. There's charged electrons in there. So just for this top two bullet points, don't worry the bottom two. Those are important. So based on his experiment, his discovery, he made a new model of the atom. He called it the plum pudding model, where he thought that you had these plums, these solid particles that were electrons, but he couldn't find a positive particle. And so he said, well, it doesn't exist, that there's not a positive particle, you have positive jelly-like substance. And so within the atom, you have this positive jelly, which you see in red up here. And then you have floating around the jelly, you have these solid electrons that are in blue. And that was his guess about the atom and what it would look like. And so he developed this without knowing about protons or neutrons. It didn't last very long because he discovered protons pretty quickly after this. Yes. So Ernest Rutherford, so the model of the atom is always changing. Even still to this day, we're making revisions to what we think the atom looks like because we can't really see it. We don't have a picture of an atom. We have to make our best guess about what it might look like.
So are most of the revisions getting closer, do you think? or no?
We think so. I mean, as far as we know, we don't know for sure, but it seems like we're getting closer and closer to what the atom really looks like.
Is it possible for scientists to be completely wrong?
It's possible, yeah. Yeah, because we're human beings and, we don't know everything and we can be really wrong about something. I mean, there was a time we thought the sun moved across the sky. We saw the sun move and to our eyes, that's what was happening. But now we know the sun does not move. I mean, so there are things that can seem obvious to us that actually don't exist that way. So we could be wrong. Ernest Rutherford, after Thomson, did further experiments to see what was in the atom besides just electrons. And what he did is he took a box of radiation. This emits alpha radiation, very small positive particles that he was bombarding atoms with. And on this one, I guess pretty much everything on here.
Oh,
You don't need to draw the picture, but just the main, I guess probably helps draw a picture too. Because you should know what he's doing here. You can make a rough sketch and a rough idea. Let me go through this with you all, but yeah, this is important to know. So you should either write down each of these words or draw a picture, but understand this experiment. So this box of radiation, it's positive radiation that's being emitted and shot through. He chose gold foil because it can be very, very thin.
So is that radioactive box, is that positive or negative?
The box,
Yeah.
the box itself is neither. It's lead, but the green beam is positive. And so he shot positive radiation at the gold foil. And he chose gold foil because you can make it very, very thin. You can make it just a few atoms of thickness. And so he knew it was almost 1 atom in thickness that he was shooting the beam at. Based on Thomson's model of the atom, they should shoot right through. Because what Thomson said is that you have electrons, which are very, very small, and then you have positive pudding, positive jelly, and that's it. So alpha radiation, because it's positive, would be repelled by the positive jelly, in which case it would shoot right through and do nothing except go all the way through. So it's like shooting a bullet through paper. It should just go right through with no deflection, very easily pass through. What he saw happen though astounded him, because what he saw happen was that the beams were deflected. They would deflect downward, they would deflect back at him. How did he know this? Well, he got this zinc sulfide screen right here. When alpha radiation hits the zinc sulfide screen, you can see it light up and it glows. And that's how he knew that the beams were going backwards, they were being deflected based on where it lit up on the zinc sulfide screen. And he said this is like shooting a bullet through paper and the bullet going back in your face. Like, it just does not make any sense. So what was happening? Well, there must be very large particles in the atom that were shooting the beams back at him. So he concluded that there must be a large particle that was causing this deflection. And it must be positive because positive repels positive. So the positive alpha beams must be deflected by the positive center of the atom with a large particle to make that happen. So-
Basically, he was saying that there were things so large in the atom and so solid that they could deflect.
That's right. Not just that they were large, that's one thing, but also they were positively charged.
Oh.
And so they were large and positively charged because positive repels positive. So the alpha beams are positive. So only positive would repel positive. And so we discovered the proton. He discovered a large particle that was positively charged in the atom. Let me show you a video just to further, what now?
I still need to keep like.
Yeah, just really quickly. I mean, I can go back to this too after the video, but I want to show the video too to help you understand this a little bit better. I think you get the idea, but just to make sure you do, the video should help. So that's how they discover particles. They don't really see them directly because they're too small to see, but they can do experiments like this where they conclude, well, this must be a particle based on the experiment.
So now did they think that it was like a rock with pebbles stuffed into it?
Yeah, kind of. Yeah, that's a good way to think of it. Yeah, that is kind of what they thought. No, Rutherford said more is just like there's empty space between. Like that's more of what he thought. It's like that this was a sun in the middle with planets orbiting around it with the electrons. That's more of what he thought.
So he was kind of right.
Yeah, he was. He had a lot of right ideas about this. All that was really missing in his model is that the neutrons. That was the biggest thing he was missing.
How thin can you make gold foil? Like how many atoms?
You can make it down to a single atom of thickness. You can. It'll look like transparent. Like it'll look like gold saran wrap. You can see through it. even thinner than gold leaf.
Is that what they put on food?
They can, yeah, they can put very thin gold flakes on food. You can eat gold.
Do they make it more than an atom thick?
Oh yeah, they do. Yeah, if you can't see through, it's more than 1 atom thick. But what's nice about gold is you can make it very, very thin and it looks like a lot when it's really not. And so that's why they can put gold flakes on food and it's not incredibly expensive. I mean, it still is, but compared to what you might think it would cost. I don't know what it would taste like. I'm assuming. Have you had gold before? So you've had gold?
I thought you can buy the actual sheets of gold
You
really
can.
cheap, but the stores just sell it crazy expensive when they put it on food.
Well, I mean, yeah, they mark it up, that's for sure. Yeah, they do. Like a gold sheet, like you get like a postcard for about $2 or so. Like a postcard size sheet of gold would be about $2, which is still pretty expensive, but compared to what you might think it is, it's not that outrageous. So yeah, gold is not cheap. But they put it in drinks, they put it on food, all kinds of different things.
They sold like a pizza for like $2 million.
And that's ridiculous.
Yeah.
Let me show you a video of his
But they have the
experiment.
whole pizza, not just the slice.
Just really quickly. I'm just not gonna make it full screen. Yes, we will. Looks like it's going to be, oh, actually I didn't make it up yet, never mind. But probably Thursday or Friday before your break. I haven't made it for sure yet. Okay. Let me show this to you really quickly.
1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So that just shows you just an animation of what his experiment showed to him. I think we'll stop here for now. On page 114, work on question 7 through 11 for right now. On page 114.